Okay. The last lecture was called potential energy, but I never actually defined potential energy because it went a little long, or took a little bit longer than I thought, but that's okay. Because those are the big ideas. If you understand how forces can do work on an object and the net work done results in a change in the kinetic energy, that is the heart of anything regarding energy. Now let's look at some particular forces where there are some more interesting properties about energy related to gravity and springs. So, particularly, we saw before that I could throw an apple into the air, and I think with the numbers we had, that I initially gave the apple 5 joules of kinetic energy. It rose into the air. Gravity eventually drained away all 5 of those joules. But then the apple returned back to my hand, where gravity ended up giving the 5 joules back. And even when I threw the apple into the air, and then the apple rolled down a ramp to get back to my hand, it still got back the exact same 5 joules of energy. And you can imagine we could have a wiggly ramp that goes up and down multiple times, like a bumpy roller coaster. And if it's just gravity, no friction or anything like that, then the apple will return back to my hand still with 5 joules of energy. There's something interesting going on there, where what gravity takes away, it eventually gives back. So we'll see this is the idea of potential energy, that energy can be stored away and tapped back into. Let's start with a quick just example review. Suppose there's some crate with mass m, and you lower the crate at a constant rate via a rope. What work is done by the cord over some distance delta y? So in this case, if I had to look at it, I would first draw a picture like I've already done. It's some box on a rope that gets lowered some distance delta y. It has some mass m, and I say that you're lowering it at a constant rate, which suggests that the magnitude of the velocity vector is a constant. If mv squared is constant, which if m and v are constant, mv squared of course is constant, the change in kinetic energy as the box lowers must be 0. The final kinetic energy must be exactly the same as the initial kinetic energy. So in that case, by the work energy theorem, I would say the change in kinetic energy, since that is just equal to the net work being done. But in this case, the net work is the work done by gravity and the work done by the tension rope. Because there are 2 forces acting on the system. And particularly, these 2 forces are acting either parallel or anti-parallel to the motion. They're not perpendicular to the motion. So then that implies that the work done by the tension force must be exactly equal and opposite as the work being done by gravity. Whatever positive work gravity is doing, why is it positive? Because gravity points down and the direction that the box is moving also points down. So I would expect gravity is doing positive work. If the cord were not there, gravity would make the box speed up as it fell to the ground. So to prevent it from gaining speed or from the kinetic energy from growing, the cord has to cancel it out. The cord has to do opposite work, negative work, which again makes sense if you look at the force body diagram, or the free body diagram rather. The tension force points up while the displacement or the velocity is pointing downward. They are moving anti-parallel to one another. I would expect that then the tension force would do negative work. So we've seen before that in this case gravity does mg delta y. It goes down some distance. It will do some positive work equal to mg delta y. The tension force must therefore be doing negative work equal to negative mg delta y, so that the sum add up to 0. All right. Let's consider our apple again. Think of the examples I gave at the very beginning. I throw the apple up, and then either it falls back down, it slides down a ramp, or maybe it takes some zigzagly wiggly path as its way back down to the ground. We actually did the first two cases where for a 0.1 kilogram apple with an initial kinetic energy of 5 joules, it rose up, gravity did negative work, and gravity did positive work as it came back down. In all of these cases, it was only gravity we had to worry about doing work. You might think, what about the contact force? When in the case that there was a ramp, recall that if the box is moving down the ramp this way, the contact force points perpendicular to the surface, our ramp, which makes a 90-degree angle with the direction the object is moving. So therefore, the work being done by the ramp is 0. Again, relating to that the work is the force dotted with the displacement. And since they make a 90-degree angle, the dot product, remember, is 0 in that case. And then if the ramp is wiggly, it doesn't matter because at each point, the contact force of the ramp always points perpendicular to the ramp. And as long as the box is not losing contact with the ramp, then the motion will always be perpendicular to the surface force. So in all those cases, we got K final of 5 joules when it returned to your hand. So we would say it appears that gravity, or the work done by gravity, displays path independence. It does not matter the path that is taken. In all three of these cases, from the apple going from the top to the bottom, the same amount of work was done by gravity during those paths. And we could try to quickly prove this path independence using the assumption that we saw that in these cases, the work we did throwing the apple up into the air, we were able to get back. And in this case, for these examples, it appears like it doesn't matter how you get back. In all of those cases, you ended up getting the same amount of work or energy back as was lost. So I claim if we know that, say, the work done from going from point 1 to point 2 equals negative the work done going from point 2 to point 1, then there is path independence. Let's said another way, I guess. Sorry, this is saying that if you have closed loops such that the sum of the work being done along your loop equals 0, you get path independence. Let's see what I mean by that. Suppose I have some point A and I have some final point B. One way to make a loop is I could say throw the apple up into the air, it reaches some highest point, then the apple falls back down, for example. Another path could be that I throw the apple up into the air, it reaches some highest point, but then it goes through some intermediate steps as it makes its way back down. Maybe it's a ramp, and maybe it's something else, but take some different path to get back to where you started. The closed loop assumption says that the work done from A to B plus the work done from B to A equals 0. It's the black curve. And then the work done from A to B plus the work done from B to C plus the work done from C to A equals 0. That's another loop that I've drawn out. And so the question then is, let's see. I guess the question is something like, is the work done from A to B the same as, say, the work done going from, like A to C and then from C to B, for example. I could go directly from A to B, or I could take an intermediate route, some different route to get to B. Is this a result of the fact does this occur because of the fact that closed loops are 0? So I guess I should put a question mark there. Well, I guess one way to see this then is perhaps this is kind of straightforward, because the first inequality says that work from AB equals the work done from B to A. So then if I plug that into the second expression, that says negative the work done from B to A plus the work done from B to C plus the work done from C to A equals 0, which implies the work done from B to A equals the work done from B to C plus the work done from C to A. And pretty straightforward. No matter, as long as your closed loop is 0, it doesn't matter the path you take. You can take any path to get from your starting point to the end point. It doesn't matter. It could be as simple, it could be as complicated as you can imagine. And why am I re-emphasizing this again and again? Because the strength of energy and using energy to argue things rather than using forces is because we can just look at where we started and where we ended, and it does not matter how we got there. It does not matter how complicated the situation is between these 2 points. We can say something about what has happened if I simply know where I started and I simply knew where I ended up. This is not true for all forces, of course. This was true for gravity, and if we did this again for springs, we would find it's true for springs. This is not true for, say, friction. Friction, if friction does negative work, take air drag. Air drag can be thought of as a friction. I throw the apple into the air. There's air drag that works against the motion of the apple, so air drag takes away energy as the apple goes up. But then as the apple falls back down, air drag is again still going in the opposite direction of motion. Air drag continues to do negative work even when the apple goes down. So you do not get it back. Air drag does not give back the energy it took away when the apple is moving in the opposite direction. We say that a force is conservative if there's path independence, or if the net work along a closed loop is 0. most of you will not see this until Calc 3, but a way to write this down mathematically is we would say, we would write something like this, that the work done on the force, where this kind of squiggly circle on the integral means for a closed loop. It means you're doing some integral where your starting point and your end point are the same. Examples of conservative forces: gravity, elastic springs, the electrostatic force, which will be the first thing you learn in Physics 3, are all examples of forces that have this conservative property. Whatever it takes away along part of the path, it can give back if you end up back where you started. We can think of these forces as forces where energy can be stored away. And used later. You can potentially get it back if you need to. An apple gets thrown into the air, gravity takes away energy, but gravity gives back that energy when it falls back down. So these conservative forces, if we think back to our analogies we had on the whiteboard, where my analogy of conservation was, right, you have some amount of cash in your pocket, and if you withdrew money from an ATM, which goes into your savings account and takes money out, you end up with more cash. Then the analogy is you have some sort of kinetic energy, and there's positive work done by a conservative force. You can think of it as that for that force, you're tapping into some reservoir of energy that is free to be exchanged between kinetic energy and being stored away. And so you get more kinetic energy as a result. Versus the opposite, where you have cash, and then if you deposit money into your account, you ultimately have less cash on hand, but you have cash that is now stored away and can be accessed later. The analogy there is that you have some sort of kinetic energy, and then negative work is done by a conservative force. You, at the end of the day, have less kinetic energy. But that energy was not destroyed. You can think of it as being stored away in some sort of energy savings account that you can get back later on. So there's this reservoir of potential energy that can be tapped into for conservative forces. So we define potential energy. Usually it's kind of, I think your book uses U as a potential energy, where we define it as, like kinetic energy can be some number between 0 and infinity, I guess. It It can be some positive number that represents how much energy you have currently, kinetic energy you have currently in your motion. Then you could think if some of that energy got taken away by a conservative force, some of that energy would have to get that would be because negative work is being done. Negative work is being done, kinetic energy is going down. Gravity, for example, is draining away some of that kinetic energy. And then it puts it into some other reservoir, which we'll call potential energy U. So if kinetic energy is taken away, the potential energy should then go up. So we define the change in potential energy for a conservative force as negative the work done by the conservative force. All right, so for a conservative force, for example, what kinetic energy is lost by negative work? That means W is negative. Negative W is then positive. As a result, the potential energy increases. If the apple, say, is falling down, gravity is doing positive work on the apple. As a result, the kinetic energy is increasing. And you think that it's increasing because it is accessing and it's cashing in some of its savings and taking out from the potential energy bank. So then potential energy goes down. The work is positive, so negative W is negative. And we can see this kind of graphically. Right, so here is some interesting skater ramp where there's only gravity at play, there's no friction, so it's just gravity at play here. And we have our little skater, which we're going to place onto the ramp and let them do their thing. But we can think about the energy that is potentially available from gravity in this case. When the skater is on the ground, it is as low as the skater can get in this case. Gravity cannot do anything to make the object continue to speed up. When the apple was high in the air, there was potential for gravity to make the object fall down. There was a place for the apple to go. Once the apple is on the ground, gravity, try as it might, can't get the apple to go any lower. There's no more potential energy to be accessed. Versus if I raise the skater into the air, notice that there is potential now for gravity to do something. There is a reservoir of energy that can be turned into kinetic energy in this point. So then if I put them on the ramp and let them go, what happens is as the skater falls down towards the ground, that is gravity doing positive work on the object, cashing in the energy savings from the bank. The amount of energy in the bank goes down, the kinetic energy goes up, your cash goes up. When the skater is rising into the air, they are moving against gravity. So gravity is slowing down the skater. As a result, gravity is doing negative work on the person. And as a result, some of their kinetic energy is being taken away and put into savings. It's being put into a savings account where if it's possible, that energy that was taken away by gravity can be accessed again. And in this case, since gravity is a conservative force, this can go on indefinitely. To tease what's coming, you can notice that the total energy, kinetic plus potential, and I guess plus thermal as well, but there is no friction here, always remains the same. Simply, there's an oscillation between how much energy is in kinetic versus how much energy is in gravitational's potential to make an object move. Now I could add some friction. And notice what's happening is that friction is always doing negative work. And as a result, some of that energy is getting lost and cannot be tapped back into. They cannot access that thermal energy once it has been converted into, say, heat between the wheels and the surface. They can't get that back and turn it into motion. So kinetic and potential still oscillate between one another, but as time goes on, the total amount of energy they have to turn into either gravitational potential, or kinetic decreases. And eventually the skateboarder comes to rest at the bottom. That would be an example of a non-conservative force. But if there are only conservative forces, this could go on forever. But not today. So this is an example like what we saw before, where you have your system, and if the force that is acting on the system is just simply the conservative, or the forces that are doing work on the system are only conservative forces like gravity, it seems inevitable. It seems that there can be a clean kind of exchange between kinetic and potential. Let us actually write down what that is for gravity. For gravity, the change in potential energy is equal to negative the work done by gravity. But we saw that that's just, a force over a displacement with the gravitational force. And we saw in the case of the apple that whether or not it was the apple just falling straight down, whether it was rolling down a ramp, whether it was whether or not it was taking some weird path, it ultimately just became, in this case, negative, and that was negative mg delta y. If the change in height was from a high height to a low height, that's positive work. Delta y would have been negative in that case. And then if it was going up, delta y would have been positive, and gravity would have done negative work. That is just kind of summarizing what's in here. That's the work done by gravity. So in this case, we can define the change in potential gravitational energy as mg delta y. I'm going to gravity mg delta y. Let's see, I think that deserves a highlight. Tell me how the height of the object is changing. I'll tell you how much work gravity has done. Does not matter whether it's a ramp, straight up and straight down, or some other weird path. It only is just mg delta y that determines the amount of work that gravity was done. And I think we did that example for the ramp last time. I guess the thing to point out here is that notice that it's really only changes in potential energy that matter. I'm writing delta U, not just U. It is the work that's being done by a force results in the potential energy changing. Either you're putting stuff into savings or you're taking stuff out of savings. There's no real physical meaning to say that the absolute potential energy at a certain point is something. It's really the only thing that matters physically is the fact that potential energy changes when work is being done. Things have to go somewhere. Things might have to speed up or slow down. There has to be some amount of work has to be done in order for potential energy to change. And again, this can be equal to 0, greater than 0, less than 0, depending on what's going on. If you're working against gravity, you would expect this to be negative. If you're working, you would expect the work to be negative, the potential, the change of potential would be positive. The work is negative. It's slowing down the object, taking that kinetic energy, storing it away, so the amount of savings you have, your potential energy increases. To do it as a bar chart, if we want to do that. Again, we could take the apple as I throw it into the air. It started with some with some kinetic energy. And then as I threw it into the air, I could imagine that it started with no energy in savings, no potential energy. But then as it soared into the air towards its highest point, the kinetic energy reduced down to 0, and the potential energy that was available from gravity increased to some non-zero value. And then as the apple fell back down to the ground, the exchange then flipped. All that potential energy went back. There was, the potential energy decreased back down to 0. Again, because gravity was doing positive work, which speeds up the object. Or you can think of it as taking stuff out of the potential energy reserve. And so the potential energy then decreased in that case. And then similarly, I could write similarly for springs. We saw that the work being done by the spring was either plus or minus 1/2 the spring constant, and something like delta S or delta X, whatever it is, how much the spring compressed or stretched back out. So in that case, I could define a change in potential energy from the spring as something similar, right? 1/2 K, and I might call it, say, delta X squared or something, if I wanted to. All right, so this might look something like 1/2 K, right? X final squared minus 1/2 K X initial squared, or something like that. Which again, this could be positive, negative, or 0, depending on what the spring is doing. Really, again, don't just blindly take the math equation, right? You know what it generally should be, 1/2, some change in position squared. Yeah, I guess I could be more careful here. Maybe instead I would write 1/2 K delta X squared or something instead. And in that case, again, it's, if the spring is doing positive work on the object, the spring is pushing the ping pong ball out, the ping pong ball is speeding up, positive work is being done. You could think, where is that kinetic energy the ball is getting coming from? You can think of it as being you're cashing out the potential energy savings you have that was stored, of energy stored in the spring. So the final thing to say here is that if your system only has conservative forces, doing work on the system, then you get what we call the conservation of mechanical energy. And what do I mean by that? Suppose you have a situation where you have only conservative forces acting on the object. And you want to study how the kinetic energy is changing. Maybe it's a roller coaster where you're starting at the top of the tallest hill and the roller coaster ends at the very bottom. And the only thing that really is doing anything to the roller coaster is gravity. Doing anything, I should be more exact. Shame on me. The only force that's doing work on the roller coaster is gravity. There's, of course, a contact force with the roller coaster, but that's not doing work. So then if I wanted to say what is the change in kinetic energy of that system, I might say, okay, well, I know from the work energy theorem that the change in kinetic energy equals the net work that's being done on the system. Right, which in that case might be, the sum of the individual forces that are doing work. If there's only one force, I can write that simply as just that it's being done, say, by, I'll take gravity as the example. The change in kinetic energy is from the work that gravity does. However, the work from gravity can be thought of as a change in potential energy from gravity. That is just a definition. So as a result, that's saying the kinetic energy, the final kinetic energy minus the initial kinetic energy equals minus the change in potential energies. So minus the potential energy at the end, minus the potential energy at the beginning. And then through a little bit of rearranging, you can write down something that looks like this. The kinetic energy at the end plus whatever potential energy is at the end is exactly equal to the kinetic energy at the starting point plus whatever the potential energy was at the starting point. Which again is saying that I can look at what is the state of the system at the very, very beginning of, say, the roller coaster, the cart going down the roller coaster. The roller coaster could be infinitely complex, but I know it then gets to the end of the roller coaster at some height, with some speed. I can figure out exactly what those things are just based on knowing my starting point and my end point. So this is kind of our first version of the conservation of energy. Conservation of energy, COV, says that with conservative forces, the total energy does not change. Kinetic plus potential at the beginning equals kinetic plus potential at the end. There is no difference in the overall magnitude of their sum, which is pretty great. That is actually quite a useful and powerful statement. And this is kind of our first example of conservation. Let me do one example, and then the next lecture will be many more examples. Suppose I do have that roller coaster. And you start at some height h. Maybe you start at rest. All right, so your initial velocity is 0. And then you end with some final velocity that is pointing to the right after you go down and up and through some bumps and whatnot, and we'll assume it's a nice frictionless roller coaster. And your cart never loses contact with the roller coaster. It's a safe roller coaster. I could ask, how fast is the roller coaster car moving at the end? Now, doing this with Newton's laws would be a mess. You'd have to know the exact shape of the roller coaster, kind of what is going on in terms of, how each of those hills and valleys are shaped. You would have to take into account, both gravity and the normal force, through a variety of different angles. Or we can identify the fact that there are only conservative forces. There are only conservative forces doing work here. Namely, in this case, gravity is the only force that's doing any sort of work. The roller coaster itself is not doing work because the contact force is always perpendicular to your motion. So then you can say the kinetic energy at the top of the ramp plus whatever potential energy you have at the top of the ramp, whatever energy you have in savings at that top, must be equal to the kinetic energy at the bottom plus whatever energy might still be in savings at the bottom. Maybe you didn't turn it all into potential energy. Maybe you did. So kinetic energy is simple, but how can we define these individual potential energies? We said before that the change in potential energy is negative the work done by gravity, which was mg delta y in this case. Which you can think of as mg, y final minus mg y initial. And for delta u, or for this, you can think of as the final potential energy minus the initial potential energy. And so then you might think, well, a reasonable thing to do is to just identify this as this, and this as this. And that would be good, and that would be perfectly appropriate. Again, since it's only really the change in potential energy that matters, you really only care about how the potential energy has changed overall. But typically, and I think your book takes this, your book defines the potential energy at a point as mg y at that point. Which is fine and good, but you have to be careful because well, you don't have to be too careful, actually. I guess this is saying something. It's saying it's making a choice and saying that the potential energy is 0 at y equals 0, which is perfectly fine. Your book talks about this. It's called, it's selecting a reference point. In your system, your coordinate system, you're saying, okay, I'm going to say the potential energy has some value equal to 0 at y equals 0. Which is fine because, again, it's only changes in potential energy that matter. So whether you call y equals 0 where it's 0, or maybe I could say plus 100. So I could say at 100 meters, that's when it's 0, or I guess it would be negative 100 meters is where it's 0. Doesn't matter since it's only the changes that matter. But I kind of like the idea of using y equals 0 as where the potential energy also equals 0. So let's adopt that. Maybe it's worth a little highlight. So then the conservation of energy really is just saying that I could say 1/2 m the initial speed squared plus mg the initial height equals 1/2 m the final speed squared plus mg the final height, which is 0. And then similarly, we said that it's starting from rest, so this is also 0. This is 0. You can then immediately say that mgh must equal 1/2 m v final squared. And the m's cancel, and you get that the final speed, in this case, equals the square root of 2gh. Again, appreciate how useful this is. I could have drawn any roller coaster that started at a height h and ended at the ground. It does not matter what goes on in the middle, as long as you don't, say, fly off the roller coaster or anything that would obviously cause non-conservative forces to be at play, like you slamming into the ground or something. Whatever happened in between your starting point and end point didn't matter. You can immediately write down that the final speed you have when you get to the bottom of the roller coaster is the square root of 2gh. Which is pretty cool. Let's see, where am I on time? Yeah, we could do the ramp again as well. That might be. So suppose I have my apple, it's up here at 5 meters, m is 0.1 kilograms. It rolls down some wiggly ramp. And I could ask, what is the speed when it gets to the bottom of my of the ramp? Well, again, we can think what forces are at play: the contact force of the ramp and gravity. The contact force of the ramp does no work. So only gravity is doing work on the system. Gravity is a conservative force. Sorry, I'm realizing I'm just sitting here flipping off the screen. And that, as a result, energy is conserved in this case. Mechanical energy is conserved. And by mechanical energy, I really just mean the energy associated with motion. Really, it's just an exchange of potentials with kinetic energy. We'll write down a more general version of the conservation of energy next lecture. So again, I can say 1/2 the mass of the apple times the initial speed of the apple squared plus mg, the initial height of the apple, equals 1/2 m, the final speed of the apple squared, plus mg, I guess the final height of the apple. And in this case, we're defining it as, it ends at 0 and it started from rest. So notice again, you get the same sort of answer. The velocity of the apple would again be 2gh in this case, or the square root of 2gh. You can also see, if we just called this the final kinetic energy, you could also plug in m, little g, and h, which we saw before when we were doing work, was 5 joules. That again, the final kinetic energy is equal to 5 joules, which was, if you remember the entire problem, the original problem was we threw it up with 5 joules, 5 joules got robbed away from gravity, but then gravity just gives it back. Which again is the idea of conservative forces. You can store stuff away in potential energy, you can get it back